Welcome to this lecture series in linear algebra. We are starting a new module in which we will discuss linear maps. And in this lecture, we will define just what a linear map is and look at some examples. So we need to be familiar with or very clear about the concepts discussed in the first module. These are the topics that we discussed in first module, and we need to know everything properly. Let me not get into the details of any of these and continue directly. So, what is a linear map? So first of all, when we say a vector space, we will always mean a finite dimensional vector space, despite the fact that a lot of what we will say will also apply to non-finite dimensional vector spaces, but I don't see any point discussing those. So unless otherwise mentioned, we will always assume that vector space means a finite dimensional vector space. Alright, so now fix two vector spaces V and W over a field F. Then a linear map or a linear transformation, just two different terminologies meaning the same thing, from the vector space V to the vector space W is a map from V to W such that two things happen. First is that T of x plus y is tx plus ty. So when I write tx, I mean t of x. Okay, let me write t of x. T of x plus t of y. It looks very, very ugly. No, it looks ugly. So I will write tx plus ty for all x and y in the domain. And t alpha x is alpha tx for all x in the domain and alpha in the base field. So a linear map is a map which respects the addition operation. So it kind of distributes over the addition, and it respects the scaling operation. That's all. So that's a linear map. As of now, it is not clear why one should define such a thing, but as we learn more and more mathematics, we see that there is a general notion of morphisms. Whenever you have a collection of objects, like in our example, vector spaces, there is also traffic between the objects. So you can think of objects as cities and these morphisms as traffics. This is the traffic. This is what lets you go from one vector space to another, sort of. Think of it that way, and this is a central theme in mathematics. All right, so that is a linear map, and yeah, let's continue. So this is a notation. The set of all the linear maps from V to W is denoted by this notation HOM V comma W. Just a matter of notation. HOM stands for homomorphism, but we don't need to know that. All right, and once you have V equals W, we write end V instead of HOM VV. This is perfectly fine. One can write this, but we will write end V, and this is read as endomorphisms. So endo meaning self, and morphism is basically a map, self map, but in the context of vector spaces. So all linear maps from V to V, not just any map from V to V, but linear maps from V to V. So just some pieces of notation. In textbooks, you may not necessarily see this notation. Like in Axeler's book, I think he uses LV comma W. That's okay. I think I will stick to these ones. Okay. So let's move on and discuss examples. Most important thing, examples. So define this map from R2 to R2 as the map which sends this coordinate pair to this coordinate pair. So note that this fixes that guy, and it doesn't fix this guy. All right. So since it fixes that guy, it also fixes any scale of that guy. So entirety of the x-axis remains fixed. So let's see what is the image of R2 under T. So the entirety of x-axis will remain fixed. And let us say this is the origin. Origin will obviously go to origin. Maybe I should mention that. So if you have a linear map, it will take origin to origin. I mean, it will take the 0 vector to the 0 vector. So note T of 0 is 0. Why is that? The reason is T0 plus 0 is T0 plus T0, but 0 plus 0 is 0, so we get T0 is equal to T0 plus T0, and that implies T0 is 0. So any linear map will always fix, or well, I shouldn't say fix, it will always take the 0 vector to the 0 vector. Okay, so origin goes to origin and everything here gets fixed. That's okay. What about that guy? What about the vertical line? Well, this particular point, which is 0, 1, that thing moves to 1, 1. So 0, 1 moves to 1, 1, and you will see that this entire vertical line will be tilted. So just convince yourself that the vertical line, the y-axis basically starts looking like that. And further, if you compute what is the image of that guy, the image of that guy is now this. It is a shift of the y-axis and so on. So this is how the linear map changes the shape of your domain space. Unfortunately, there are too many lines to draw. Maybe I will copy paste. Oops. So, I mean, you get the idea, right? Let me not draw everything. So these lines will be tilted like that. So what we see is that the linear map in this case shears the space. It is stretching the space in some way. So just to get a feel for what a linear map does. Okay. More examples. Define a map from R3 to R2. Of course, the two spaces can be different. So define the map this way and check that T is linear. Doing these simple exercises helps us understand, or rather digest a notion, become more comfortable with it. So that is a linear map. Now define something from R2 to R, both are of course vector spaces, as this Tx, y to x plus y plus 1. Now this is not a linear map. This is not linear. One way to see it is not linear is that it is not taking the 0 vector to the 0 vector. It is taking the 0 vector to 1, which is non-zero. So this is not a linear map. Also, consider this example, R2 to R, which takes x, y to this guy. This takes the 0 vector to the 0 vector, but this is certainly not a linear map, and I leave that as an exercise to you. Not linear. Generally, quadratics will not be linear. So this is not a linear map. This is a nice example. Suppose we have two non-empty sets, one contained in the other, and fix some field f. Define the map T, which takes this from which has this vector space as its domain and that as its target. Define that as T of f. So let me just say f maps to f restricted to x. Let me explain a little bit. So what is it doing? It is taking a map which, so f is a map from, let me draw it that way. So f is a map from y to the base field. Maybe I'll use phi because there are two f's. So let me use the symbol phi. So it is taking the map phi to this guy, to that thing. So phi restricted to x is basically the map which you get when you restrict phi to x. So you have a point in this space. Think of it as a point in y and apply phi. That's all. So that is phi restricted to x. So you take this guy to that guy. That's what I mean here. And T is a linear map. So T is linear. This is very easy. Let me just maybe try to write down the steps for summation. So T phi plus psi is by definition phi plus psi restricted to x. But when you feed something from capital X, this by definition is this, which is by definition of addition of two maps is that, which is phi restricted to x fed x and psi restricted to x fed x, which is T of phi of x plus T of psi of x, which is T phi plus T psi of x. So T of phi plus psi, this is T of phi plus psi. If you feed x to it, it's same as feeding x to this guy, and therefore this is actually equal to phi restricted to x plus psi restricted to x. This is something trivial. I'm just writing it out in full detail to confuse you. So this is a linear map. Restriction is a linear map. This is the restriction map, nothing more. This is the restriction map from this space to that space is a linear map. That's all that we are saying. All right. Okay, this is a nice example. U be a subspace of a vector space V. Define the map T as, this will look funny, Tx is equal to x for all x in U. So once you have x in U, this is also a member of V, so it is legitimate to just pick a member here and send it to itself. Okay, and this is a linear map. So T is linear. Just check that it is linear, and if you think about it, it is nothing but the inclusion map. So whenever we have two sets, let's say A contained in B, we have the inclusion map from A to B, which just takes little a to A for all A in the space, in the set A. So that's a purely set theoretic thing, and this T is nothing but the inclusion map. So the inclusion maps are linear. If your domain is a subspace of the parent space, then inclusion maps are linear. That's all this is saying. And take this as a simple exercise if it is not immediately clear. Okay, the second one is also very important. I mean, it's the fifth one in our chronology. So this time we have three vector spaces, U, V, and W, over some common base field F. So all three of them are vector spaces over some common base field. And we have two linear maps, one from U to V, the other from V to W. So then we can compose them as we discussed in the, as I have discussed in Kickstart on functions. You can look at that playlist. There is this notion of composition. So first you apply, maybe I'll use a different color. So first you apply T, then you apply S. So this map is called the composition of S and T and denoted that way. Right? You start with U, you hit it with T, and then hit that with S. That thing is denoted, that composite operation is denoted this way. And the thing is that this guy is also linear. So let me just check the addition one. So how do you check that? S composed with T of x plus y is by definition S of T of x plus y but t is linear, so this is s of tx plus ty. But s is also linear, so this is s of t of x plus s of t of y, which is s composed with t of x, s composed with t of y, and that's it. So this checks that the composite respects the addition, similarly scaling, and therefore the composite of two linear maps is a linear map, of course, when you can compose them. Not any two linear maps are composable. They are composable if the target of one is the domain of the other. So the composite of any two linear maps is again a linear map, and that's a very nice fact. Okay, so here is the most general example. Given any two vector spaces, there is every linear map looks this way, the way we are going to describe. So fix two vector spaces, V and W, again they are finite dimensional as we mentioned. All vector spaces will be assumed to be finite dimensional unless otherwise mentioned. So these are finite dimensional vector spaces over some common base field F. Fix two bases. So let V1 up to Vm or V1 up to Vn be a basis of V and fix a basis for W. Once we have fixed these bases, here is what we want to say. There is a unique linear map. Sorry about that. So this is a basis of V, but this is just some list of some vectors. Sorry about that. So fix some n vectors, W1 up to Wn be any vectors in W. Right, so we have a basis for V, but we have just chosen any vectors for W. So then what we want to say is that there is a unique linear map from V to W such that okay. So once you have a choice of once you choose where to send the basis elements, you get one linear map. You get at least one linear map which respects that choice, and exactly one. Okay. So another way to say this thing in a diagrammatic fashion is, suppose we choose a map from choose any map from this set to that set, where of course this set is consisting of the basis vectors. What this map is corresponding to is basically FVI is WI. But in this diagrammatic thing, just choose any map from this set to that set. Then of course there is this inclusion map to V. And what we are saying is that there is a unique linear map T. There exists unique T linear which makes this diagram commute, meaning whether you go this way or you go that way, it's the same thing. So I've just repeated what I said here in a diagrammatic fashion. This may look contrived or convoluted first, but these diagrams really help. One should be comfortable with these diagrams. Commutativity just means that either you directly travel this way, meaning you have to respect the arrows. So from here you can take this arrow, or you can take this arrow and then that arrow and reach the same destination. There will be no conflict. These two paths will always reach the same destination. So Vi maps to Wi, and what we are saying is that there is a unique linear map T which also maps to Wi under this composition. So why is that? Why is such a thing true? This is not a mystery, but we shall give it some time. Okay, so first we should prove existence. So to prove existence, will be by construction. So just define T from V to W as by declaring T of alpha 1 V1, this being equal to, or I should say via, this is equal to alpha 1 W1 plus alpha n Wn for all scalars. Okay, so this is our recipe. This is how we define the map, but there is a problem. I mean, there is no problem, but one should note that we need to show the well-definedness of this map. Now, since v1 up to vn is a basis, for any vector v, there exist unique scalars alpha 1 up to alpha n such that this is equal to v. And now, basically, we are choosing a representation of v in terms of the chosen basis. And using that representation, we are defining our map. So I just wanted to make that very, very clear that once you, what you want to do is for each vector v, you want to decide what is T of v. So once you pick a vector v, first you find out the unique scalars alpha 1 up to alpha n such that this linear combination is equal to v. There exists such a unique linear combination only because this was a basis, not just some spanning set. And now once you have this representation, using that representation, you define the image of what this is. Okay, so this is a well-defined map, and now you just check that this is linear. That is like a very, very easy thing. Check that T is linear. And clearly, what is T of V1? T of V1 is T of 1 times V1 plus 0 times V2 plus 0 times Vn, which is 1 times W1 plus 0 times W2 plus 0 times Wn, which is W1. So TV1 is W1 and similarly TVI is Wi, and therefore it does, this proves existence, that indeed there is at least one linear map which respects the image that we chose for each basis element. What about uniqueness? Okay, let's see. That's also very, very clear. Basically, if you've already decided what V1 is going to, there is only one choice. If V1 is mapped to W1 and V2 is mapped to W2 and Vn is mapped to Wn, and if T is linear, we are forced that this better map to that. Because, again, this is something that perhaps I should have said, but if you have a linear map, okay, maybe I'll make a box here. If T is linear, I'm saying something very, very general, then T of alpha 1 V1 plus ... and let me use x. Alpha 1 x1 plus ... alpha n xn is alpha 1 tx1 plus ... alpha n txn. This is for all vectors x1 up to xn in the domain and alpha 1 up to alpha n in the field. So this is just induction. If n were equal to 2, then this is true by the definition of a linear map, but you just induct and that same thing is true for any n. So what I'm saying is, this was anyway forced. If you want a linear map which sends V1 up to V1 to W1 ... Vn to Wn, then this was anyway forced. So there is only one linear map with that property. So stay on this for as long as needed to get comfortable with it. This is very important. All right. So now we will look at the notion of linear isomorphism. Okay, so let V and W be vector spaces over a field F. a linear isomorphism from V to W is a linear map T from V to W such that there is a linear map in the opposite direction satisfying S composed with T is the identity on V, and T composed with S is the identity on W. So T goes from V to W and S goes from W to V. So we are insisting that this is identity, and S goes from W to V. T goes from V to W, and we are asking that this also be the identity. So if that happens, we say that T is a linear isomorphism. Okay. So it's unclear what we are trying to capture, but let me say a few more things. So first of all, note that a linear isomorphism is bijective. So note that any linear isomorphism is a bijective linear map. Why is it a bijection? Well, by definition, these two things force that it is a bijection. Okay. But here is the point. Any bijective linear map is a linear isomorphism. Any bijective linear map is a linear isomorphism. So bijective linear maps and linear isomorphisms are the same concept, even though I haven't defined it that way. I haven't defined, the way I defined a linear isomorphism is somewhat convoluted, but there is a reason behind it why I did it that way, even though it could have been defined in a much simpler or apparently simpler way. Okay, let me just say one thing before I continue. A linear isomorphism is also called an invertible linear map. So this is also called invertible linear map. All right. Yeah. So we will look at the proof of this, but what is being captured here? What is a linear isomorphism trying to do? Linear isomorphism is just saying that the vector spaces V and W are same in some sense. The behavior of addition here is just carried forward to the behavior of addition there, and the behavior of scaling is also carried forward there in a way that does not lose any information. So T is in some sense just changing the names of V and making it look different, but the behavior amongst the elements of V is the same as the behavior amongst the images of the elements of V. So a linear isomorphism gives you a recipe to think of elements of V as elements of W. Okay. A linear map may be losing information, but a linear isomorphism preserves information. So information preserving linear maps are linear isomorphisms, if that makes sense. Okay, so why is it that any bijective linear map is a linear isomorphism? You pick a bijective linear map. So here I'll just not write the full details, but here is the thing. So if T is a bijective linear map, so let okay, and we want to show that it is a linear isomorphism. Just define S as the inverse of T. Okay. So then we will show that S is linear. All right. So So we want to show that S is linear. So let W1 and W2, I will just check the addition property. Want to show that okay. So since T is a bijective linear map, it is in particular surjective. So say TV1 is W1 and TV2 is W2. Then by the fact that T is linear, we have this is the case. And therefore V1 plus V2 is S W1 plus W2. Why is that? Because if T of something is something else, then S of something else is something. That's what it means for S to be T inverse. So we have that, and just simply because TV1 is W1, we have SW1 is V1. So V1 is SW1, and similarly V2 is SW2. So we do have the equation we wanted to show. And similarly, you can do the scaling version. So I did give full details. Yeah, so any bijective linear map is a linear isomorphism. And we discussed the philosophy behind isomorphisms. Okay, all of that is very important. And I think with this, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.